All right, welcome to the AMC10 Basic class, and please do the fun problem of the day that's being screen shared right now while we wait for more people to come in. All right, I'm going to go. All right, I'm going to go over this now. So the area of a rhombus is the one half the product of its diagonals. So if the diagonals are lengths A and B, then the area is one half AB. And this is because the diagonals of a rhombus are perpendicular to each other. And now you know that the area of the rhombus is 210 square inches. And you have that it's two consecutive integers. And sorry. Okay. And now you have that the area is 210 square inches and the diagonals are two consecutive integers. So you have that the larger one is 21 and the smaller diagonal is 20. And I guess you can see this because 210 is 21 times 10 and 10 is one half of 21 minus 1. And so the rhombus looks okay. The rhombus looks something like this. And each of these is half of one of the diagonals. So this is 10.5 and 10.5, and this is 10 and this is 10. And so from here you can apply the Pythagorean theorem. And that just tells you where if one of the side is s, then it tells you that s squared equals 10.5 squared plus 10 squared. And when you expand this, you get that it's 100 plus 110.25, which is 210.25. And this happens to equal 14.5 squared. So S is or 58 inches. All right. Are there any questions? All right. And this week, most of you who submitted the homework did well on it. So we're not going to cover any of the homework problems from last week this week. And so we'll be moving straight on to the contents. And so this is our only week on geometry. So this might feel a bit rushed. So we're going to cover triangles, what similarity means, lengths, analytic geometry, and finally 3D geometry. And so triangles. For here, we're just assuming that you already basically know how to do these. So we're basically not going to cover much in the first bit. Yeah. So try to do this problem. Alright, so we can do this problem bit by bit. So, first of all, let's focus on triangle ACD. So we know that from the first sentence of the problem, we have that AD equals DC. So these two are equal. And that tells you that the two angles marked like this are congruent to each other. And so if you let both of those be x, that's an x, 2x plus 140 equals 180, and so x equals 20. Now, now we can do almost the same thing for triangle ABC, except this time it's the angles marked like this. And we can let each of these be a and a, or whatever variable you want. And then so 2a plus 40 equals 180. And so a equals 70. And now angle BAD equals angle BAC minus angle DAC equals 70 minus 20, which equals 50. And so the answer is 50 degrees. Are there any questions? All right, here's another example for you to try. Alright, I'll start covering this problem. So, you know that segments BD and AE intersect at C, obviously. Okay, and now you have that AB equals BC equals CD equals, sorry, CE. C. And you have that angle A is 5 halves of B. And so the sum of the angles, okay, first of all, we can see that triangle ABC is isosceles because these two are equal. And so, come on. And we have that these two angles are also equal. And so the sum of the angles of triangle ABC, angle A plus angle B plus angle BCA is B plus 2 times 5 halves B equals 180. And so angle B equals 30. And so angle C equals 75, which is also angle A. But angle C is more important from here. And so angle BCA is 75. And since angle BCA and angle ECD are vertical angles, so they're congruent. And now you have that the measure of angle D and E are congruent because, like triangle ABC, triangle ECD is isosceles as well, with EC equals CD. And so angle E equals angle D equals X. And so 2x plus 75 equals 180. So x equals 105 over 2, which equals 52.5 degrees. All right, are there any questions? All right. These two are two examples of special right triangles. And you probably should memorize these or at least know where these come from. And so this one, the one on the left, is known as the 30, 60, 90 right triangle for pretty obvious reasons. And one way you can remember this is that it's half of an isosceles triangle, like this. All right, I'll redraw that. This H and 1/2 H. And the one on the right is known as an isosceles right triangle. And that's because it's isosceles and also right. And another triangle you could consider special is the equilateral triangle. And that's where all these sides are equal. And in the case of triangles, all three angles are also equal. Okay, so here's the example for special triangles.
What is E? Where's is E? Where is E?
All right. I believe it's come on. Okay. I believe at this point it's just that the shaded area blocked it out.
Oh. Oh, okay. So it's that point. Okay.
Yeah. Okay.
Okay.
Oh, and if you couldn't tell, R is the shaded area. All right. So I've gotten a complaint that that someone can't see the screen. So I scrolled it all the way up, and that's also because I'm in the process of writing the solution. All right, I'll just start going over this problem. So, okay. So the area of R can be found by taking the area of this large rectangle. All right, you can see it, and then subtracting off the area of this pentagon that is shaded in green. And so we can find the area of the pentagon. And to do that, we can break it up into two pieces, as shown here. And so one of them is an equilateral triangle, and the other is a rectangle. And now we can first do the rectangle. And so this side is from 1/3 to 2/3, so it has length 1/3. And so now we can look at this. Okay, you probably can't see that here. Okay, whatever. And so now we can look at this 30, 60, 90 right triangle. And then in this one, this side is 1/3, and the vertical side is square root of 3 over 3. So this side is square root of 3 over 3. And so the area of the rectangle is root 3 over 9. And now for the equilateral triangle. So clearly the base is 1/3, and the height, by using the properties of a 30, 60, 90 right triangle, the height would be 1/3 times 1/3 divided by 2 times root 3. And so that's root 3 over 6. And so the area is 1/2 times 1/3 times root 3 over 6, which is root 3 over 36. And so the area of R is 1/3 minus square root of 3 over 9 minus square root of 3 over 36, which is equal to 1/3 minus 5 root 3 over 36. And if you want, you can put this over a common denominator, and this just simplifies to 12 minus 5 root 3 over 36. All right. So now similarity. And so first of all circles are similar. And there are three main ways of determining if two triangles are similar. If any two of the corresponding angles are the same, then the triangles are similarity by the AA similarity theorem. And this is because of the fact that the three angles of a triangle add to 180 degrees. Because knowing two of them, you can find the third. And now, two triangles are similar if all their corresponding sides are in an equal ratio by the SSS similarity theorem. And similarly, if two of the triangle's corresponding sides are an equal ratio and the corresponding angle between the two sides are equal, then the triangles are similar by SAS similarity. And two polygons are defined as similar if their corresponding angles and are equal and their corresponding sides are all in the same ratio. And for polygons with four or more sides, both of these conditions are necessary. And all right. So where did I cut off? Can someone tell me where I cut off? Can someone tell me where I cut off?
When you were explaining the two polygons,
Okay,
um,
okay, thanks. So two polygons are similar if their corresponding angles are all equal and the corresponding sides are all in the same ratio. And note that for polygons with four or more sides, both of these conditions are necessary. For example, you can't have that all the corresponding sides are in a fixed ratio and meaning that all the corresponding angles are equal. And this is not true for polygons with 4 or more sides. And the reverse is also not true. But for triangles, by AA similarity or by SSS similarity, you have that you only need to fulfill one of these conditions for the other to also be satisfied. All right. And now triangle congruence. It's when two triangles have same sides and the same angles. And this is the same. And you also have congruent polygons, but congruent triangles are by far the most useful parts. And so you can use SSS, SAS, ASA, AAS, and in all of these, S stands for side and angle sides. A stands for angle. And here, RHS, or more popularly known as hypotenuse leg theorem, and it only holds true for right triangles. And so SSA is not sufficient for congruency because it may make two different triangles. And later on, you may learn when SSA is actually enough, but for now, you don't need to know this. So here's a problem with similarity. hear me? Sorry. Can you hear me?
Good.
Yes.
Okay.
Fine.
All right. So I'll just start going over this problem. I wasn't talking before. Hold on. Okay, there we go. Close. Okay. So you know that. All right. So we know that AB equals 13, AC equals uh I don't know what happened there. AC equals 5 and BC equals 12. And so you also know that CM equals CN equals 4. And J and K are the feet of the perpendicular. So you know that BN is 12 minus 4, which is 8. And AM is 5 minus 4, which is 1. And so you also know that BKN is similar to ACB, and that's because they share this angle, and both of them are right triangles, so you can use AA similarity. And you can do the same thing for AJM and ACB, and because they share angle A, and they're both right triangles. And so NK is 40 over 13, that's 4. And BK is 96 over 13. And you have that AJ is 5 over 13 and MJ is 12 over 13. And so the area of pentagon CMJKN is the area of ABC minus the area of BKN minus the area of AJM, which is 5 times 12 over 2 minus 5 over 13 times 12 over 13 divided by 2 minus 40 over 13 times 96 over 13 over 2, which is what's written here. And you can do all the calculations, and when you simplify it, you just get 240 over 13. So are there any questions? All right, so length. So for lengths, we're going to cover four main things, which are the Pythagorean theorem, the angle bisector theorem, Stewart theorem, and mass points. So I'm going to assume all of you already know what the Pythagorean theorem is. So here's your first example. All right, I'll start going over this now. So you have that AB is 3 and BC is 4. And you have that, come on. Okay, this is trying to write a 4. And you also have that angle ABC is a right triangle. And so you can apply the Pythagorean theorem. This is a pretty bad 3 actually. And so you have that AC is 5. And now you also have that, what? Okay, AD is 12 and DC is 13. And by the converse of the Pythagorean theorem, which basically says that if a squared plus b squared equals c squared, then it forms a right triangle. Then, so you have that this is a 90-degree angle as well. And so the area of the quadrilateral is 3 times 4 over 2 plus 5 times 12 over 2, which is 36. All right, are there any questions? Okay. Angle bisector theorem. So the angle bisector theorem states that in triangle ABC and angle bisector AD, where D is alongside BC, then you have that C over M is equal to B over N, as in this diagram. And it also tells you that C over B equals M over N. And you can treat either of these as basically the angle bisector theorem. And the converse of this holds as well. Basically, if this is true or this is true, then AD is an angle bisector. And you can use this to find a theorem for finding the length of a angle bisector, but this needs Stewart, which we'll cover later. If you want, you can see the formula here, written here. All right. So here's your first example. All right. So first of all, we can draw a diagram. So A, B, and C with angle bisector D, and BD is 2 and CD equals 5. And so by the angle bisector theorem, you have that this is 2x plus 5x equals 10, which means x is 10/7. And so AB equals 20 over 7, and AC equals 50 over 7. Yeah, it's pretty short. All right, are there any questions? All right, so Sewer theorem. So you usually probably won't need to use this, but this is pretty useful to know still. And if you really want to use it, you don't try other methods first. And so basically what it says is this. And the labeling below, using the labeling below. And yeah, the standard labeling is triangle ABC and opposite sides AB of length ABC. That's the standard labeling for triangle lengths. And so you have that b squared m plus c squared n equals amn plus d squared a. And you can write it as man plus dad equals bnb plus cnc. And so the most popular mnemonic for this Stewart theorem is a man and his dad put a bomb in the sink. So really the hard part for Stewart's, memorizing Stewart's, is that you need to memorize where A, B, C, D, and M and N correspond to. Oh, that's a bad A. Anyways, yeah. And there's a couple of proofs for Stewart's, but they're all pretty complicated or long. They're all pretty long or complicated or stuff. And so, mass points. So, mass point is basically a way of finding ratios of length. That's basically what it's normally used for. And so you basically assign weights. And you can put a first weight anywhere you want with any value that you want. And normally the most common method is just put one such that all ratios should work out to basically be integers or so. And so from the first weight, you can find others using a couple of rules. So if 2 points balance, then the product of the mass and the distance from the line of balance of 1 point will equal the product of the mass and distance from the same line of balance of the other point. And if two masses are balanced, then the point on the balancing line used to balance them has a mass equal to the sum of the masses of the 2 points. A short example here would be like, say that these two are equal. Sorry, these three are all equal. And so a random weight you could assign is a mass of 1 to C. And so you can chase around like this 1, 1, and then this is 2, this is 2, this is 2, and this is 3. And that tells you that AX over XZ would equal 2. And that's just like a short application of how mass point works. All right, here's one for you to try mass point on. All right. I got a request for to see the slide again. So I'll just pause share here. All right, I'll start going over this problem now. So first of all, you know that the first sentence, you have that AD and CE are medians. And so BD equals DC and BE equals AE. And so you can assign a mass of 1 to point B, like shown here. And then from there, because D is a midpoint, so C is also 1, and D has mass 2. And similarly on AB, point A has mass 1, and point E has mass 2. And the intersection of AE and AD has mass 3. And since point D has twice as much mass as point 1, so PA is twice of PD. And since PD is 2, so PA is 4. And similarly, you can do the same thing on segment CE, and that tells you that CP is twice of PE, which would then be 3. And so since one since the sides of triangle PDE are 1.5, 2, and 2.5 by the converse of the Pythagorean theorem, you have that angle DPE is right. And so the diagonals of AEDC are perpendicular to each other, and one of the diagonals has length 3 plus 1.5, while the other has length 2 plus 4, and so the area is 1/2 of their product, which is 13.5. All right, so are there any questions? Okay, so power of a point. So there are three main cases for power of a point. The first case is when the two lines are chords and they intersect inside the circle. And in this case, AE times CE equals BE times DE. And another case is when one of the lines is tangent to the circle, while the other is a secant. And in this case, AB squared equals BC times BD. And if both are secants, as in this case, CB times CA equals CD times CE. And this applies even if both are tangents, but that just tells you that the side lengths are equal. All right, so here's an example for power of point. All right, I'll start going over this now. So you want to find the value of x. And so you can directly apply power of a point. And that tells you that 3 times 3 plus 5 equals x times x plus 10. And now you have that this is equal to 24. And this is x times x plus 10. And so if you expand this out, you get x squared plus 10x minus 24 equals 0, which means x equals negative 12 or 2. And now clearly negative 12 is ridiculous because you can't have a negative side length, so x is 2. Any questions? All right. So areas. So for a triangle with side lengths ABC, the area can always be found by using the following formula. A equals square root of s minus a times s minus b times s minus c, where the semi-perimeter s is equal to a plus b plus c over 2. And this is pretty important. Now, shoelace formula. So this works for the area of any polygon with n vertices. So you can see what so if the polygon has vertices A1, B1 has these vertices, come on, has these vertices, then the area is just this. And so you can always go counterclockwise order, but that's unimportant because you're finding the absolute value. And it's called shoelace because it looks like this when you pair them up. And that looks like a shoelace. And you can also write it in this form, where I think I've gone over what the summation notation means. If not, it basically just means you just I is a dummy variable and you just plug in 1, 2, 3, 4, 5, 6, 7, 8 all the way up to n. All right. So here's an example for areas. All right, I'll give a hint. So actually, it's basically two hints. I won't write them down though. So tri- you can see that triangles AFH and CH are similar, and you can also see that triangles CEJ, and GJA are also similar. And you can do this to solve the problem. All right, it seemed like this was a pretty hard problem, so I'll start going over it. So, by the similarities I told you, triangle AHF and CEH, you can see that FH to EH is 2/3, is 2 to 3, and that's because AF is 2/3 of EC. And you can also do this for triangles. Hold on a second. Some different color. Whatever. All right. You can also do this for triangles AJG and CEJ. And in this case, it's JG to EJ is 4 to 3 because this is 2/3, because AG is 2/3 while EC is still 1/2. And so the area of triangle EHG is the area of triangle EFJ times EH over EF times EJ over EG equals 70 over 6, which is the area of EFG, times 3/5 times 3/7, and this is just equal to 3. And you can prove that the area of triangle EFJ is equal to the area of triangle EFG times the ratios of the two split sides, basically. You can prove this, but I won't cover why it's true now. It should be pretty intuitive though. Alright, so circle area stuff. So the area of a circle is pi r squared. I think all of you should know that. A line that just touches a circle is called a tangent, and a line that cuts the circle at 2 points is a secant. One that goes from one point to another on a circle is called the chord, and a chord that passes through the center is the diameter, and part of the circumference is called an arc. And so a sector is a slice of a circle that basically uses two radii and the arc between them. And the slice made by a chord is called a segment. Yeah. All right. So area problem one. All right, come on, draw. All right, so here you can see that this is 3 and this is 3, and you can pretty easily see that this is 45 and this is also 45, which means that this is 90, which means that this is a 45, 45, 90 right triangle. So this is 3 root 2, and this is 1, and this is 1. So the area of the square is 3 root 2 plus 2 squared is 18 plus 4 plus 2 times 2 times 3 root 2, which is 22 plus 12 root 2. Pretty short problem. All right, so, oops, that's way too far. Okay, here. I'll explain how to solve analytic geometry problems while showing you this problem. We probably won't have the time to actually do this problem, by the way. All right, so analytic geometry. Basically, some of the basic stuff is, say this has center AB and radius R, and this is a circle. So the equation is x minus a squared plus y minus b squared equals r squared. And the basic way of a line is form of a line is y equals mx plus b, where this is b and m is the slope. And another way is if you're given the slope and the point x1, y1, so y minus y1 equals m times x minus x1. And the first form is known as slope intercept form, and the latter is known as point slope form. And now rotations in the Cartesian plane go, the 90-degree rotations are probably the easiest. And so going counterclockwise, here's what they are. XY, negative y, x, then negative x, negative y, then y, negative x, I think. Yeah, should be right. All right. This is going counterclockwise, and the reverse order for clockwise. And reflections across the line x equals y, just if the original was AB, then the new one is BA, and across x equals negative y is almost the same, except you have to include a negative. All right. And we also have 3D geometry to cover, so I'll also cover this pretty quickly. So these are the basic shapes of 3D geometry. And these are the volumes for a triangular pyramid, cylinder, cone, square pyramid, rectangular prism, and sphere. And the surface areas is 4 pi r squared. This one you should know. This one is 2 pi rh plus pi r squared, 2 pi r squared. Sorry. The surface area of a cone is a lot harder, and I'll need to self-derive this. Oh, r squared plus h squared, and 2 pi r. It's basically it's basically like you can think of it as unfolding the cube, and when you unfold the cube, I believe you basically get that it's pi r squared plus pi r times h squared plus r squared. I think that's what you get. All right. And so you can think of And another way you can solve these is by basically like taking the cutout kind of like you can think of unfolding a net. For example, this is the net of a rectangular prism, and the net of a cone would look something like this. If you sorry, the net of a cone would look like a sector if you exclude the circle, and the net of a tetrahedron would look like this. Yeah, and you can see the problem here if you want. And I think I'll just quickly outline for a second how you do this because it's really short. So you just look at the net of the regular tetrahedron and you just look at one midpoint to the midpoint of the opposite edge, which in this case happens to be here. And these are both 1, and this is a parallelogram, and these three are all parallel, so this is also 1. Yeah, really short problem. Okay, all right. I guess that's it for today's class, and thank you for coming. You you can see the homework, and we'll put up homework and other stuff like that in a few within a few days. Yeah. Oh, and by the way, there will be class next week, and the 2 weeks after that there will be no class. We might host an event during those 2 break weeks though, so keep an eye out for that. Yeah. Bye. You can leave now, I guess. Thank you for
Okay,
coming.
bye.